Alrighty, so Sonja is going to talk to us about sampling, learning, and coloring. Take it away.
All right. Hi. Am I unmuted successfully? I think so. Okay. So I was volunteered at the pub to say something that I was gonna say at the beginning of this talk. So I'll give just a shorter version. That I have never worked with Frank on a math paper, but I have seen him at many conferences, and this started when I was a graduate student, and I really appreciated his support. One sort of a social, we are all human way is, where is this picture? Here we go. This is a picture from Banff last year. I believe this is Frank. Anton, you're in this photo, though you forgot you went skiing with us. I'm on the side. I'm not the anti-social mathematician. What I am is a mom with 2 kids, therefore have no ski poles, have a really hard time turning around and then flopping down the mountain. So I'm on the side, and in a sense, it's kind of nice that I was like the slow, awkward one, because whenever me or my husband fell down, which we did because we're not so good at this, he made sure to wait for us. So there was no math involved during skiing, but there was lots of humanity, and I think that's just what Frank does. He just makes sure to wait for you, even if you forgot your poles. Okay. Exactly. That's exactly what you said. That's exactly what you said right there on top of the hill. But there's some pro skiers on the picture, so I'm just grateful. The other thing that I wanted to say that I remember about Frank, and this has changed the way I think about mathematics and PR or marketing. I don't think we're often very good at this. Elizabeth Gross asked me one time, how do you explain to people what you do in plain words? I'm like, I don't know, I just don't. This is a horrible answer. That's not a good answer, right? It's a bad answer. But Frank has a good answer, and he told me, not to me, he just said this somewhere at the conference. He said, this is a great area to be in, because what I do is I solve systems of equations. That's what my mom or my grandma or somebody thinks I do.
I'm the only person in this room who does what their mom thinks they do.
I'm the only one who does what their mom thinks. And so which I think is incredible, because now I like that sentence, I don't think he was trying to badly to do PR, but it just resonated with me, because now my 6-year-old says, Mommy solves equations. He knows what that means, kind of, sort of, whatever. Okay, we don't do math like that, but like these are English words that make sense to people. And so I tried that. And so, Sonja, what do you do? Oh, I compute toric ideals. Since 2003. Like, it's not working well for me. So I've spent some years trying to figure out, why am I computing toric ideals? Because that's all I'm really doing. Combinatorics and toric ideals in the background. And so I finally found an answer in statistics. So here is my what I do slide, but it really drives the, why is this algebraic statistic, which Jose introduced 2 days ago in his wonderful talk, why algebraic statistics make sense to people to talk to, and why, how algebra is really an integral part of this. So this is a horrible graphic that is lifted from the New York Times, hence the bad resolution. This is a really old, I guess by now, article. It's called Inside Japan Incorporated, and it's a picture of a network of share ownership. So this is actually a directed graph. Sorry, edges, like arrows are so small. So there's a graph from, there's an edge from Sony Electronics to Fuji Media going that way, which means there is a share ownership from here to here. And the Prime Minister of Japan at the time when this was written, Shinzo Abe, complained about his country's economy. And he said, to paraphrase, y'all just invest in each other, because he invested in me, I'm going to invest back in him. That's a horrible idea. We should diversify Japan. Without making any political statements, I gave this talk in Japan. It went great, okay? So just I don't want to take sides, but I do want to take a mathematical side. So the question is, does Prime Minister Abe know algebraic statistics, or did he just look at this picture and say, y'all are way too weirdly connected to each other in a bidirected way? So, I am like a non-expert, okay, cross-holding, sure, but that makes sense. So how do you look at a data set like this from the New York Times or from anywhere else and say, is this expected, or is this extreme in the Shinzo Abe sense, extreme? A more relatable, maybe, data set that you might want to think of that relates to the open problem I presented yesterday is you think of a number, a three-dimensional table of mathematicians where one dimension is their gender and cannot be binary, so the open problem is not open. So one dimension is gender, one dimension is, I don't know, rank, and one dimension is salary. So is there any so gender should be independent of salary. Prove it, right? So this is more relatable, I think, to people in this room, but this is sort of the picture that looks better on the slide, so that's the running example. So the question is, how do I do statistics with this? So I think like a statistician, and this takes some time to sell, by the way, this idea. How do I think like a statistician? Buying shares is a random event. I know it's not random. I just mean there's a probability model, there's a probability, and we are trying to understand what's this probability. I'm a very rich person, I just like to buy shares. I have a probability of buying shares, I go around and buying them. Okay, so in that sense, random. And so the New York Times article suggests that this probability of buying shares is governed by something called reciprocity. I know you called it cross-holding, but reciprocity is a statistical term for this kind of a model. So you own shares in mine, so I'm going to buy in yours. Okay, that influences my probability. And so how do you think like a statistician? You come up with a statistical model that captures exactly this idea. And then I want to produce relations to data using this reciprocation effect, and then I turn that effect on or off to figure out whether the model, the data fits the model, okay? And so can I adequately explain how the share ownership was generated? And so so what does this have to do with algebra? So my entire last few years have been consumed by, Markov bases. I will give a definition. But the idea is Markov bases are an algebraic object, but they're really a statistical object. They come from this application. They help you design a sampling scheme of a carefully chosen reference set of share buying scenarios. In other words, you have 17 corporations, and you want to understand what are all the possible scenarios between those 17 corporations so that then you can make a conclusion, okay? That's the why of Markov bases, not the what. So how it works in practice is you open up a laptop, you plot that same graph just with numbers in R, and then you run the AlgStats package, of which Luis is a co-author. And what, if your example is small enough, this will actually run. So I'll talk about that. So you assume that buying shares is governed by reciprocity, and then you are trying to figure out whether the data you observed is unusual or not. So if it is unusual, then, this is what the reference set looks like, and your data set is way out there, so it doesn't fit. Or if it's usual, this is some kind of a measure of fit, or goodness of fit statistic. I'm not telling you what it is, but this is what the data is, and your data, this is what the sample is, and your data is the red point, so then it would fit. So these are pictures on top. We have, when you do not have a reciprocation effect, the model doesn't fit on the bottom, and when you do have a reciprocation effect, the model fits. So this is a proof, and I only put quotes in proof because mathematically, what are we talking about? But statistically, this is proof. If I have some guarantees about my algorithm, that Prime Minister Abe was actually correct. It is unusual to have that many what did you call it? Cross-holding. Sorry, I forgot the word, yeah. Right. So I can do this. It shows that he's correct. Oh, I'm picking a side, okay. Which one? Yeah, I am rejecting the null. Yeah. So the null is, everything is fine. We are not reciprocating. We're operating as a unbiased operation, and I reject that. Sorry, okay. Sorry, thank you. This is Canada, so I have to say sorry for things I'm not supposed to apologize for. Sorry. Someone dropped an iPad on the streetcar this morning and dropped it, and we all looked. And he said, sorry. I'm like, it's your iPad. Sorry, I said a story, okay. I'm married to a Canadian. I'm entitled to these jokes. Okay. So here are the main characters of the story. So what I have is a large, possibly sparse integer matrix A. I really have a hard time with the pointer. So I'm going to look at the top left box right now. I have a large, possibly sparse matrix A. This is the linear matrix for the linear map I presented the problem yesterday that counts somehow the flattenings of your large tensor. What's a tensor in my case? Well, the 17 by 17 by 2 by 2 telling me where the edges are in which direction, okay? And such a matrix uniquely defines as something called a log linear model. So I invite you to just Google this later, okay? So it's just a model in statistics that has a very special shape, E to the inner product of parameters and columns of the matrix. So in other words, the matrix tells you everything you need to know about the statistics, okay? Then we define something called a fiber of that matrix. So for a given right-hand side B, which is the summary of my table X, I'm going to find all the values X, all the possible data that could have had that same summary. Right? So B in statistics is called a sufficient statistic because it suffices to summarize the data if the model were correct. So in a sense, when you're saying, oh, I'll give you another example later. Okay. And then I have the kernel of this integer matrix, and every element of a kernel is called a move. So here's a small, tiny picture of a matrix. Oh, this is a large sparse matrix, 3, 4, 5. Okay, one row. It needs to fit on the picture. So if you look at what is B? B is 15 here. So if you look at all points X in Z3, such that 3x1 plus 4x2 plus 5x3 equals 15, you get these black points here. And in order to move between the points, I need something that when you multiply by A, you get 0. So those are the 3 different basis vectors in 3 different colors over there. Okay? If you change B, you have a different fiber, right? Because I have more points that I can fit in. I have a lot more black points, but my 3 colored vectors still connect all of those points. Okay? So I can the fiber is just a set of the black points. When I choose a set of moves that help me explore this fiber, this is called a fiber graph. That's this colored graph inside of the tetrahedron. And then the definition of a Markov basis is that it's the set of colored moves that connects this for all B. Infinitely many B's, right? This is super frustrating in statistics because nobody knew that this set even exists or is finite. However, it's just a generating set of the toric ideal of A. So we know it's finite. And so this is a celebrated theorem from 1998, which there's also a backstory. I talked to Percy Diakonis about some problem, and I say, you know, this theorem has, you know, really changed the field. And he said, you know, it's interesting because I talked to Bernd, we figured it out. He said, it's obvious, I proved it. And then Diakonis apparently spent another 4 years trying to actually finish the paper. Because in statistics, it's highly non-obvious how you actually use this. I'm not saying Bernd gave up. I'm just saying in math, it's like, fine, it's just a generating set. But to actually use this is really non-trivial. So this talk is mostly about why is it so hard to compute a toric ideal? And why do you actually not want the full toric ideal? And which part of this makes sense in statistics? Okay, that's why I'm still computing toric ideals. Because even though it's in grad school, it's actually a sea of problems that are still open. And so this theorem tells you that you just have to find the A corresponding to those 17 incorporations, plug it into Macaulay 2, and it will burn because it will not compute. There's 17 choose 2 times 4 indeterminates. I don't know what that is, but it doesn't run, okay? And so, but we know that the Markov basis exists for any log linear model. I have connected chain, I have convergence. I can do this with the data. There's not 1,000, but close to 1,000 citations of this paper on whatever. I think I checked on Google Scholar or something, okay? So there has been too many papers if you think that this is just a simple theorem, right? Why are there so many papers? Because I cannot compute 17 choose 2 times 4 indeterminate in any software. Actually, not even in 42, which is the state of the art for toric ideals. And so people have tried to figure out what is the set of moves I actually need for this family of problems, what are the structures, and I cannot possibly give an overview of all of those. But I'll give you one really nice, paper. This is Adrian Dobra, 2003. Dobra is a statistician who, wrote down that something called a decomposable hierarchical models possess a minimal Markov basis with one norm equal to 4. So he classified these sets of statistical models that are very nice and recursively defined, and these are all quadratically generated toric ideals. And if you do the translation, you'll discover you actually know these ideals. Okay, so I invite you to sort of look that up. Okay, so somehow, don't worry, it's complicated, but there is a recursive algorithm if you can just decompose your model and then build up the generators so you don't really need Macaulay 2 in however many generators, however many variables that I mentioned. I think 544. Yeah, I can't, okay. 544, I have a really hard time with any number beyond 3 choose 2. Like I can't compute in my head. I actually can't do it, okay. So what are all of these long linear models? Again, this is the picture I sort of drew yesterday on the board, but it was not in color. So hold on. So this was like the good news theorem. There's another follow-up work by Sullivan Stumfels. They talk about how this can be applied, and it's been used in phylogenetics for these, the binary trees in phylogenetics. It's like the same idea. You can recursively define your ideal. But the first example of a model which is not decomposable is this. It's called the no three-way interaction model. So it's the one where the summary statistics for your three-dimensional tensor are these plain sums, okay? And in that case, there is the, quote, bad news theorem. Jesus de Loera constantly complains that he doesn't want to be the bad news guy, but we keep doing it, okay? So there's a slim tables. So pick any n. You can find dimensions R and C such that R by C by 3 table, you make a long, skinny table, so one side is 3. For this model, any Markov basis contains an element with norm at least that. So this is a consequence of a powerful universality result of polytopes. So he actually, because De Loera and on, they study polytopes, so there's this theorem that says transportation polytopes are everywhere. And so you can translate the no three-way model into a long, skinny fiber of a transportation polytope. So you have the lattice, and you pick a point here, and you just so carefully pick your polytope to be so far from every other lattice point until very far away it hits, and then you have the one Markov move of that huge norm that you need to connect that fiber. This is silly, because in practice, I'm not going to get that fiber, right? But I can't prove, am I in that fiber or am I not in that fiber? So when I have a data set, I don't have a bound on how large the Markov basis is that I need. The only theoretical bound is things are bad. Any questions? Okay. The statement is, I'm going to mess it up. The approximate statement is every polytope is linearly isomorphic to a transportation polytope in a way that there's a correspondence between the lattice points.
And a transportation polytope is a fiber of such a...
Yeah. Yeah. So I think it's a few more lines long, but I don't have the notation to say, yeah. Do I have the, oh, okay. So if this is complicated, just do what people outside of, algebra do, relax. Temporarily, sorry, I apologize again. Okay, no, but, you're trying to, this, I know it's a toy example, but, I had 3 moves that I needed to get to all of the points, to connect all the points. And maybe I just gave up on my computation. I don't have all the 3 moves in the basis. I only have the 2 moves. Okay, so the yellow and the blue. And I cannot reach this point. But if you allow yourself to just temporarily step outside of the polytope, so you allow -1s in your entries, then your relaxed problem is easier. I mean, duh, right? Haven't we learned from all the other computational courses, right? So I can reach this point, but I have to pass through the red point, which is not in my actual fiber. It will give me a -1 in an entry, which means somebody invested -1 shares into, that doesn't, there's -1 people with that salary range, right? So I need to step away from that point. And so if you have studied toric ideals, you can think of these moves as like the lattice basis, so the linear algebra basis of your matrix A, because this is a rank, it's rank 1, so I got 2 vectors that I need. Then you can take that, you can saturate it. So column product of the variables to infinity. Infinity isn't really infinity. There exists a Q after which you can stop the algorithm. That's the Q. So there's a finite algorithm. If you have a tiny set of moves, you can eventually get everything. But that's a horrible algorithm, and I don't know how to stop it.
That's actually equivalent to a theorem of Petrović from 8 years before about finally generated submonoids.
I would love, so for those on, I don't know, so Frank mentioned this is equivalent to the theorem of Khovansky about finely generated monoids. I think somebody should actually write that down, because I think that will probably lead to the solution of the problem.
No, Sturmfeld's theorem.
Yes, I know, but Sturmfeld's theorem, if you can figure out what this is and then study the problem from there.
It doesn't tell you, it tells you it's the same existential question. It doesn't, it won't.
It's okay, I've given up, like I cannot solve this, but anyway, yeah.
Won't help you.
Okay.
It doesn't necessarily estimate.
So why don't I allow myself to temporarily step outside and call that a negative Q Markov basis? Because the Markov basis will connect all of the B's, and this negative Q Markov basis will connect all the B's with the relaxation, so we call that, that's a definition up on top. The only difference is the minus Q as the lower bound instead of the 0 as the lower bound. In my table, maybe 7 years ago, I said, this is not going to work. Jesus, your theorem on bad news is really bad news. And he said, prove it. I said, it's easy. You just take the universality theorem you had before and translate it to the negative whatever. And I failed to complete the proof because it's a little more complicated, because the universality theorem comes with this linear embedding that I don't quite understand. However, Delera's student, Felix Almendra Hernandez, actually went through all the details and proved that this is the bad news theorem for the relaxed problem. It says you can find a lattice basis, so the small number of vectors that you supposedly know how to compute on your computer, that you can always find an example of a family of examples where this is not going to connect even the relaxed fiber, no matter how far you relax. I mean, okay, this is exhausting. I don't want to do this. I need to connect the space, so I need to find a better way to do this. So let me tell you what are those special moves with which we usually start, and how maybe we can actually find some good news in here. So these moves that you may want to start from, which do form the lattice basis, are those, we call them, or somebody calls them, basic moves up on top. They are the moves I drew yesterday. So they are a lattice basis, and there is a thesis by a student of Rudy, this is Lee 2018, that says that if you relax to -1 and you fix the same model, no three-way, and you fix 2 dimensions, so it's R by 3 by 3 tables. So you fix 3, 3 and just let it grow in 1 dimension, then you can have a -1 Markov basis. So you can connect every fiber with this basic moves. And they left this as an open question. They spelled it out there. I think it's like a folklore by now, but it's spelled out in this reference in case people want to look it up. And we then thought, don't relax all of the elements, relax only some entries by a set. And I don't want to read this. We gave another bad news theorem that says you screw no matter what. Okay? So you just have to be super careful, because the universality theorem tells you that any fiber for any A and any B is linearly isomorphic to this transportation, no three-way model, so you can always find bad examples. Okay? It's a little bit annoying to go through the details. I'm not going to the details, but here's the picture of what Felix calls an anti-staircase subset. So basically, the summary of this slide is, this is my same definition of -Q Markov basis, but I'm only allowing entries in S certain entries in my table to be relaxed to negative. The blue, or I don't know what color this is, the blue entries are not allowed to go negative, okay? And all the other entries are allowed to go negative. The position of these entries comes from this linear embedding into the transportation polytope. And I cannot do an equation for that. But if you do this, then basically you still have the bad news. So you just have to stay away from the bad cases, and hopefully you can relax your polytope carefully, and then maybe you can hope to connect, okay? I realize this is too technical, but I have to show you a picture because this problem I thought was done 10 years ago, but it is not done. Go ahead. Yes, please. Mm-hmm.
Comparing the question of bad news here. Because I thought that you're saying that for matrices where you allow negative ones in tables, question is possible to connect all these like negative ones tables using that basic rule.
Correct. But these are, we are allowing everybody to be relaxed to -1. So that's the open question. If I allow all entries in my matrix to be, in my table, table to be, go down to -1, maybe I can still connect the space.
Oh, and greater than 0.
Correct. And here, if I fix the blue ones and say you're not allowed to relax those, then I have a problem. So my, conjecture from the bad news translates is translated into this, which is, this is just to say, don't try to, you should work on this problem by relaxing everything. Otherwise, you'll end up in one of these situations and you'll need the bad move anyway. Okay, so it's like a partial result. I put this up here because I thought I changed the slide to put less words on it, and I forgot. Okay. So Felix really worked hard on figuring out how far he can push the envelope on these results. And so I said that this example, the no three-way, is the smallest example of a non-decomposable model. A decomposable model is so beautiful. You have a divide and conquer strategy. It's always quadratic. First non-decomposable model is the worst possible case. The heck is going on? So he interpolates and says, if you have a model that is not decomposable, but I'm going to control the non-decomposable part, then you have a polynomial bound on the size of the Graver basis. So this is like an in-between result where you may have models that are really, really complicated. You only need to control the non-decomposable bit of the model, and you still can use divide and conquer. It seems obvious when I state it this way, but that's the whole point. Okay, I won't read this. I won't read it, okay. So here is what I actually want to do. Okay, so I have, looked at the no three-way model. I have, I by j by k tables. Maybe I have 17, corporations with investments. But what the heck is this? This is the actual data that I want to work on. And I should go back and say the 17 corporations data set analysis actually came out of the approach that Elizabeth and Despina Stasi, who is not here, and I created, and I'll tell you a little bit about it, but it's basically you can never use just an algebra software to do any of this. You need to do better. And so this is an example of a co-authorship network of authors. So when I said you have a large A, this is what I meant. And when you have a sparse data, this is what I meant. So this is from a now famous paper, maybe 6-7 years ago, that came out in the Annals of Applied Statistics. It collected, Ji and Jin took several years to collect and curate and publish data set on statisticians. I know it's only on like the top 4 or 5 journals of statistics, but you got to start somewhere. So they have the co-authorship network. There is an edge. Every red dot here is a person. Some names are written, but who cares? And I'm like on the boundary. I'm kidding. I don't know. I'm not in here. So this is like published between whatever year and whatever year before my existence in statistics. So it's every red dot is actually a person, and every blue edge is there when those two authors wrote at least 2 papers together. So at least 2. Why at least 2? Well, we argue that that's not a good threshold, but whatever. That's a second story. But anyway, there's way too many people in here, and what's the statistical question? What's the model? Well, how do you get a raise in your department? You say, I was cited this many times, and I have this many co-authors. So you count these neighbors, right? You're counting neighbors. You are summarizing the data set. You are implicitly, whether you like it or not, assuming there's a statistical model down here such that your summary is a sufficient statistic. It suffices for me to say I have this many co-authors that have been cited this many times, and therefore I'm good. Prove or attempt to prove that this is a good model that fits this data set, okay? I'm super interested in this. So don't, stop, yeah. There's a million questions, right? But I'm like taking a simplistic view and just starting. But I want to process this network.
So you shot me up for more co-authors?
I mean, yeah, okay. But I mean, it's funny because anyway. Never mind. I got a promotion, so whatever. So the thing that happens with this kind of data is algebra goes right out the window. And I really hate this because, when I know many of you will be or are on the job market. When you're on the job market, you say, I have this beautiful construction. It translates to this theorem, and I'm going to use it to analyze the data. And someone says, what do you do when you have 30,000 elements or 500,000 columns in your matrix? And you say, well, the computer crashes. Out the window goes algebra and your job offer. This is not like, okay, in that particular group. It's just not a good story. And I don't want to keep throwing away algebra, but if you look, this was just a graph. And if you look in the graph theory literature, people know how to take this graph and create a bunch of other graphs that have the same number of neighbors at every node. It's called a degree sequence. They do this really, really well. And so this is what Elizabeth Despin and I kind of borrowed to come up with our Markov basis algorithm. So we knew a Markov basis, but we never computed it. We do this on the fly, the way people who do this at scale would do, okay? So I say monochromatic world because all nodes are created equal. Everybody was red in the picture. And so there's something called the simple switch chain for graphical degree sequences. The KTV paper from 1997 is equivalent to saying that a toric ideal of a matrix A that has exactly 2 1s in every column, corresponding to the vertex edge incidence matrix of a complete graph, is generated by quadrics. They had to prove that. We knew that in algebra before, but the translation is missing. So everybody knows that is a quadratic toric ideal. And the beautiful thing, though, is what they work on is restricted fibers. So I'm not going to fill in this entire table with 0s, 1s, 2s, 3s, and other integers, only 0s and 1s. In that case, I go back to the picture of the bead of that fiber that I had, and I just like slice that polytope down to just a 0, 1 hyperplane. And now a bunch of connections went out the window. I need to find another way to reconnect my fiber. And so you can do this. This relates to the Grobner basis from 1995, triangulations of the second hypersimplex, because that's the matrix A. Okay? So we try to do the same. We try to reproduce all of these results for the colored graphs. It does sound like I'm switching gears. I am. I'm just trying to go through all the possible ways that we can reconstruct Markov moves and get them going at scale. Okay? Like the divide and conquer thing. So this is a great example of how you might want to do this, but there's another model called the beta SBM that I'm not defining, except for this example. So suppose you had your authors in statistics or corporations, but you color them. There are the blue corporations who work in whatever sector. There are the red ones, and there are the green ones. There are people in the annals of statistics, people in whatever, right? So you group them into communities, and then you rinse and repeat, ask the same questions. And in this world, it is unclear how one proceeds. And the graph theory has not been worked out to give us this fast sampling algorithm. And so I offer you a QR code because I'm a millennial. I don't offer you the archive link spelled out because I'm too old of a millennial to figure out to remember to do that before the talk. This is the coloring that I was talking about. Felix also proves that the toric ideal of this colored model is also defined by quadrics. However, if you want to reproduce the graph theory rapid mixing results of these simple switch chains, it doesn't generalize. So you take, you hope that these quadratic things are a Markov basis, but when you restrict to 0, 1, everything goes out the window, okay? And so I say he because Felix is the student co-author on this paper. He actually worked out all the proofs first. So he gets all of the credit for all of the proofs, although this is the joint paper, okay? I just feel like I have to say that because it's actually really true. He's not only first because it's alphabetical. It's actually, he's the first author. So he can prove, or we can prove, that you can always find a quadratic Grobner basis. And this is maybe of more interest to people who think about algebra more because this generalizes the Sturmfels-De Loera result from 1995. Because what this does is, let me go back. Where was it? Oh, here. If you get the Grobner basis for like the monochromatic world, you basically are able to solve the following problem. Find a graph of smallest cost with a given degree sequence, okay? So you can optimize, you can use, if it's a Grobner basis, there's a term order, this is a cost function. So you can solve an optimization problem over graphs with a fixed degree sequence. We can do the same over graphs with colored fixed degree sequence. So I have partitioned the vertices, and then again, I have a degree sequence. So this is a non-trivial way to generalize, but it also has applications in my statistical problem. How am I doing? Okay. All right. So here's an example of an annoying Markov move that you're going to have to make if you're trying to connect the graph on the top left with the graph on the top right. Okay? So both of the graphs on the top are simple graphs, and they have red and blue vertices standing in the middle. But if you cannot connect the two without removing too many edges at the same time, replacing by too many other edges. So think of it as every edge is a 1. Right? Every non-edge is a 0, so this is just a 0, 1 vector, and you're going to switch around, +1, -1 to move to the other side. You got to do too many -1s to go from left to right, unless you go through some double edges. So the only way to get down with these small moves is through double edges, which means you're going to remove yourself from the space where you want to be, and then hope to go back. So we are still relaxing. And we're showing that you can connect through this relaxed space, and we're showing exactly how and why this is necessary. Okay. And so to reflect on past and the future, so time out. If you're dizzy because I just presented way too many things, come back for a second. Okay. Well, there are too many things going on, and the paper that I started at the beginning is called Markov Basis, a 25-year update. And it's based on this paper with 1,000 citations, and I'm only telling you my view of one snippet of it. So of course there's a lot, but the reason why there's a lot is really, this is a quote from a paper from 1989, so ancient in stats. Besag and Clifford are very famous statisticians, and this is a quote from their paper where they use this Markov basis stuff, and they said the following. Oh, there's presumed absence of irreducibility, meaning you can't really connect this, and you're stuck around the local places. You're not actually exploring the fiber. The MCMC algorithms with Markov basis have been successful with annoying regularity. So they see that this works, and who can finally prove that you can actually do this, and how well can you do this? And they're complaining that you need a practicable method, and you need something that works in constrained state spaces. So everything that I have worked on for the past 10 years is basically, motivated by this quote. I didn't know that then, but it's, you have 0, 1 spaces. Everybody knows you can compute the toric ideal, but you can't really do it. So how do I move this along and actually do it? So this is a one-slide summary of, and so I'm going to give you 2 slides now. Each is a summary of one student's project. All of the papers are on the archive, hence you can think of this as a beer instead of coffee, I don't know. Hence the link. And all of these 3 students might be on the job market next year, which is very interesting. So Felix Almendra Hernandez from Davis, Miles Baconhus from IIT, and on the next slide, another student, I'll tell you. So what you see is a fiber. Imagine this being really large and high dimensional. It's a cartoon. And I'm sitting at a point, I cannot use the pointer. Okay. I'm sitting somewhere and I'm trying to explore all the points in the fiber, and I cannot compute the Markov basis. I only have local moves. Miles came up with a way of sampling, like exploring your neighborhood and then having your sampler learn on the go. Only compute the moves that you can apply locally and then move yourself towards the center of this polytope so you can explore a lot more. It's basic Bayesian updates in statistics. I cannot give a whole talk in one slide, but I want to advertise that if you use a Metropolis-Hastings algorithm with Markov bases on a sparse problem, this is the % unique points that you find in the fiber, and the blue one is the same problem but with the Roomba algorithm. And it works faster, so it works better, it explores more points, but it works faster because I don't have to compute the Markov basis. I compute only the lattice basis. Ivan Gvozdanovic is a machine learning student who's now working on machine learning for algebraic statistics and optimization. So if you have 500,000 columns in your matrix, which is what I gave him as a toy problem, he can just explore that fiber. He can explore the fiber, get an exchangeable sample of size 10,000 points in the fiber, or he can optimize a linear cost function and like get either near or to the actual optimum, okay? How does he do it? Well, you turn an entire fiber sampling problem into something called the Markov decision process. And so then you apply reinforcement learning. So you train an agent to say, where am I sitting and in which direction might I want to go? Let me try here, 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 and here and see if I get a cookie. So the critic, the reinforcement is, you tell the agent, here's a cookie because you went well enough, and then he keeps doing this, and then he learns provably an optimal policy for sampling these large fibers, okay? And I'm shocked that it works, but it works for 500,000 columns, which means for any of these large data sets, you can actually do it. Okay, and so this is the last slide, 21 out of 22. I don't know why that happened. There's an extra credit. So this is the QR code for the 25-year update paper, which is like an overview if you want to just have references, okay? I would not be a good editor if I didn't put down the journal called Algebraic Statistics on the last slide. If you want to learn about latest developments in this field, you can look up ASTAT, Algebraic Statistics, the journal. And actually the next issue, which may be the current issue, I'm not sure if they hit publish yet, is a collection of apprenticeship papers from the IMSI semester fall 2023 that Jose talked about. So we had this 15-week semester, lots of students and postdocs were there, and there was 1 week where they intensively worked on several problems. There's lots of papers that came out of that, okay? And also, Jose gave all my announcements, but there's a conference at Madison next July. It's the SIAG squared, so SIAM Activity Group on Algebraic Geometry. And I realized that it didn't exist, or I came along before it came along, okay? So then I realized how old I was, but this made me feel very happy to be a part of this growing community. Frank is the founding chair, and if you just look up the phrase proposal, SIAM Activity Group on Algebraic Geometry, you'll find on his website the successful proposal why SIAM should have this activity group. And if you're worried, or not worried, excuse me, if you are interested in doing better PR for yourself, either because you want to talk to your grandmother or because you want to go on the job market, I think it's a good piece to read because it talks about why the field is relevant and how it connects to other fields, okay? And it's interesting because algebraic statistics does not equal applied algebraic geometry, but they're very well integrated, and ASTAT was a part of this for all these years. And I will repeat what I said only in the one sentence at the bar the other day. that Frank's advice and support have really changed my life. And so I repeat your advice, which is apply for jobs early. If the deadline is in December, you do it in August. If the job is that.
Before the deadline.
It was August. I did it in August.
No, you prepare in August.
Yes, exactly. But anyway, no, I mean, the jobs sometimes don't come up until close to the deadline, but be ready for that job early. Apply broadly and boldly and creatively. If you can get a snapshot of a newspaper that talks about anything related to your work, you include that in your letter to explain how relevant your work is. Thank you for your attention.
Any questions for Sonja?
I wanted to check my understanding on the machine learning thing. So you have Monte Carlo Markov chain, you call MCMC, is that right? There's this Metropolis algorithm, the old one, where you do this, you decide to go in a certain direction with a certain probability. And is the essence of this theorem that you sort of update your rejection algorithm as you go along?
Yes. But you don't, so in MCMC, so the way you do Metropolis Hastings, I guess, with Markov bases is you have a bag of Markov bases, and you, in principle, select one at random, go there, or apply that move, while if it gives you negative entries, you have to throw it out anyway. If it doesn't give you negative entries, you compute the relative ratio of probabilities and then go. I shouldn't try to machine learn that, because that already works well enough, meaning that if you have the bag of moves that is guaranteed to connect, this Markov chain will mix, and if you have a good enough bag of moves, it will even mix rapidly. What we have is a tied up corner of the bag of moves. So we just have the lattice basis, because I have 500,000 columns of the matrix, and I am trying to populate the bag with more moves. So the reinforcement learning algorithm takes the lattice basis, takes a random, I said none of this, by the way, so you didn't miss it, I just didn't say it. So it takes a random combination of these simple moves, proposes a new big move and says, is this a thing I should ever keep in my bag? And then it learns that. It learns what does this bag of moves contain and what are the coefficients I should be using, And so instead of storing the bag of moves, you store these combination coefficients, which is then more efficient. So it learns the space of actions or the space of moves so it can walk around better. Yeah.
Any other questions?
So when you allow for negative ones, in my experience, once you leave the fiber, it's very difficult to get back to it. And then it's very difficult to know how much you have to run these chains to have because all those that leave the fiber you have to throw away. Is there are there any theoretical results about?
That's a great observation, and I've actually tried, I share your concern, but let me offer two things. So I did have a master student once who's like, just do it. And he's like, Sonja, it never comes back. So it is true, it's there's always a -1, I can't fix it, okay? It's just really frustrating. So there are two things you can do, well, there are many things you can do, but the two things that we are actually trying to do is, in terms of this reinforcement learning, there's actually a reward function for this agent who is learning to explore the space. And you can penalize being negative. Not disallow, but penalize. And then it can, if this is your polytope, it's doing this, but it will eventually get back in because it's being severely penalized for being outside. That's not a proof. But in principle, it should work. What happens is in this case of this KTV theorem, these are the simple moves that you take only 2 edges at a time and you find other graphs that have the same degree sequence. The proof that that chain mixes rapidly actually steps out of the fiber and puts -1 equivalently. So it screws up the degree sequence a little bit and it goes back. And so I don't have an answer, but graph theory has partial answer to some examples. So we should probably learn from, you know, when they leave, how the hell are they able to come back so fast and have a rapidly mixed chain, and me and my students are stuck outside all the time. So I don't know the answer, but there must be a way to borrow from their ideas to, like, if you're -1, reward yourself for trying to go back in some mathematical way.
Any other questions? Well, let's thank Sonja again.
Thank you.